Hello everyone, welcome to JCE Connect online classes. So in this video we are going to start about module 2 of embedded system, that is ARM Cortex M3 instruction set and assembly level programming. So in module 1 we have studied 16 types of register bank. So 16 generic registers are of 32-bit, remember. So out of 16 registers, 13 registers are called general purpose registers, and the role of general purpose register is to hold data or memory address, and that data may be either in the form of byte 8-bit or half word, that is 16-bit, or word, that is 32-bit. Other than 13 general purpose registers, we have also studied 3 special purpose registers. R13 is known as stack pointer. By default, it will be referred to main stack pointer if the processor is executing the normal program in the privileged mode, or else it is called PSP, that is process stack pointer or program stack pointer. So that will be referred only when the microprocessor is executing a normal program in non-privileged or user level. Okay, R14 register is called link register, wherein it holds the return address of the instruction when any subroutine or the function is called during the normal execution of the program. Okay, so the last register is R15, which is referring to program counter. The role of program counter is to hold the address of the next instruction to be executed. Every line of execution of the code, this program counter value get updated, get changed. Now we'll see the syntax of assembly level programming. It has a label, opcode, followed by operand 1, operand 2. It may have 3 operands as well, followed by semicolon, acts as a delimiter, acts as the end of the instruction, followed by comments. And during the execution of the program, we know that comments will be neglected. Now the label is always optional, remember. Here opcode is an instruction which is telling the software to perform one particular operation. Okay, like move, multiply, mov, mul, add, like add. These are nothing but opcode examples. Operand 1 is always referring to destination address, remember. So this is destination address, and operand 2 is referring to source address, that is this is source address. Okay, now we'll see addressing modes. So the way in which we store instructions or we represent instructions is nothing but addressing mode. Okay, so in this we are going to talk about 3 types of addressing modes. First one is immediate, second one is register, third one is memory. So we'll see immediate addressing mode. So here in this type of addressing mode, always remember the source address will be immediate value. Either it will be represented by hexadecimal value directly or by any other format, and that other format will be converted into hexadecimal and normal operation will be performed. Okay, here one more example I have taken. I have taken ASCII character of capital A. So if I write any character inside the single quote, what data will be saved? The ASCII value of that character will be saved. Okay, so let's understand these examples first. So move is the opcode, R0 is the destination address, and this immediate value is a source address. So you are moving this immediate value into register R0. Okay, so now second example, move R1, the single quote capital A. So here after the execution of this line, the ASCII value of capital A, that is 41, will be saved into R1 register in 32-bit hexa format. Okay, next third example, move followed by suffix s, R1, immediate value. Here suffix s corresponds to APSR flag set. Okay, where PSR is program status register. APSR stands for application program status register. So when any processor is executing a normal execution of the program, okay, if during the execution any flags are set, those are taken care by APSR register. Okay, now let's see register addressing mode. As the name only suggests, here you are referring to what? Both source as well as destination addresses are as general purpose registers. Okay, the movement of data is taking place between the registers here. As you can see, some examples I have written: move R1, R2. You are moving the content of R2 into R1 from source address to destination address. Source address here is R2, destination address here is R1. Okay, similarly another example: move followed by suffix s, R1, R2. Along with movement of data from R2 to R1, APSR flags get updated. Okay, and those APSR flags are what? Negative flag, carry flag, zero flag and overflow flag. Okay, now we'll talk about memory addressing mode. So basically here you are referring to what? Data movement from and to memory address. Okay, so there are two basic instructions which are referred for accessing memory. Those are load instruction and store instruction. So load instruction will hold the opcode capital LDR. It transfers the data from memory to general purpose registers, and store instruction is performed exactly opposite of load instruction, and the opcode used for this is capital STR, which transfers data from general purpose registers to memory. Now we'll understand this main memory addressing modes, that is load and store instructions. Let's start with load instruction. So I have written one instruction here. LDR corresponds to load instruction. This is the opcode for load. R5, inside the bracket R1 is written. If any content is written inside the bracket, corresponds to memory address, remember. So what you are doing according to this? You are moving the data present in the memory location of R1 into R5. Okay, now this is source address, this is destination address. So what is the memory address of this? Okay, now this table corresponds to register bank, and these values are content of registers, and this box corresponds to memory location, wherein these are memory addresses and these are contents that are stored in these memories. Okay, now so if R1 is written inside the bracket, so what is the address of R1? So going to this register bank, just check the content of R1. So this is the content of R1. This itself is referring to memory address. So going to this memory and referring to that address, in that address whatever the content is written, you are moving this content or loading this content into register R5. So register R5 is empty here after the execution of this line. So this is how this data from the memory address of R1 is loaded into R5. Now R5 is having this value. Okay, after this we'll see store instruction. So store instruction is exactly opposite of load instruction. What store instruction does? Here the content of R3 is stored into address of R1. So although you know the address of R1, that is address of R1 is this, going to memory, in that this data we have. So what store is doing? It is storing R3 content. So referring to register bank, what is the R3 content? This is the R3 content. So this value will be moved where? In the address location of R1. So address location of R1 is this. So at this already we have this data. After the instruction execution of this value of R3 will be loaded here. So this is how this data is loaded here. Previously it was this. After the execution of store, so this R3 content is moved to this address of R1. Okay, so this is how load and store instructions works. Now we'll see one more type of load instruction. Okay, so that is LDR R6, inside the bracket we have R1, 4. So here 4 corresponds to offset value. So let us talk regarding this. What is this offset value? So along with three types of addressing modes what we have discussed, we have another two types of addressing modes. Those are named as pre-indexing immediate offset addressing mode and post-indexing immediate offset addressing mode. In case of pre-indexing, so here the memory address of the data transfer is sum of the register value and the immediate constant value, that is known as offset value. So here you can see one example I have written. So LDR R0 comma inside the bracket R1 comma this immediate value. This immediate value here corresponds to offset value. Okay, so now this is written inside the bracket, in the sense this is referring to memory address. So what is the memory address here? So here memory address is content of R1 plus this offset value. So this content of R1 from this table is, let us take this. So 0x0000 0a 00 is content of R1. Okay, so to this content of R1 you are adding what? This value. So whatever you are getting after the addition, that itself is now memory address. Okay, now you are loading that memory address data into register R0. Okay, similar to store instruction. So here you are storing what? The content of R0 into this address. What is the address here? Content of R1 plus this offset value. Okay, so what I try to say here is, so content of R1 is zero, 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 a, so plus okay, that is 0x 5 zeros a 30. So this is the memory address. Okay, so this is how pre-indexing immediate offset addressing mode works. The next one is post-indexing. In post-indexing, the memory access instructions carry out the memory transfer using the base address that is specified by the register, and then it updates the address of the register thereafter. So what it is doing is, let us take one example. Load R0 comma inside the bracket R1 comma offset value. Here offset value is written as one more operand here. So normally what it does is, it does its normal load operation, okay, by neglecting offset value. Okay, so this will refer to content of register itself is the address of R1, and that value whatever is present in that address will be moved to destination address R0. After the load instruction execution completion, okay, that R1 content is updated with R1 plus offset value content. Okay, once it performs the load instruction completely as the normal load execution, R1 content is updated with R1 plus offset value. Okay, and it is same with store instruction. So I'll tell you how these values get updated by showing the execution using KEIL software. So you can see here the representation. So here LDR R6 comma R1 plus 4. So address of R1 is this, plus 4 if I do, address of R1 is what? A04, going to memory. At that A04 address, whatever the content is present, you are loading that into which register? R6. So you are loading this content into this. So this is how offset values are considered. Okay. So now we'll see another two important instructions, that is move W and move T. Here move followed by suffix W. Here W indicates word. Word is nothing but 32-bit data. Okay. So move W R0 comma immediate value. So let me tell you how this value will be saved. After the execution of this line, this data will be saved from LSB to the MSB. Okay. Now move followed by suffix capital T. Here capital T is referring to thumb instruction. Thumb in the sense 16-bit data. Okay. So after the execution of this line, how this data will be saved? So this immediate value will be saved or moved in the register R0 from MSB to LSB. So here if I write suffix W, this immediate value will be loaded or moved into R0 from LSB to MSB. So content of R0 will be like this. So this side start first, followed by this. After the execution of move T, so this immediate value will be loaded from MSB to LSB. So this side it will be loaded, not this side. Okay. If I execute these two lines of instructions one after the another and the destination register is same, then the R0 content is updated one after the another execution of these two instructions like this. So first this will be executed. So first R0 will be having this value. That time these were zeros. Later execution of this line, this will be loaded from this side, that is 3, 4, 5, 6, and these were already loaded. So totally now after these two successful execution, R0 content is this. Okay. This we have already discussed. One table I have written here which will tell you load and store instructions along with their data types. If load instruction is written with the suffix capital B, so this corresponds to 8-bit unsigned. If it is written with load SB, SB stands for signed 8-bit. Similarly it is with store. And H stands for half word, that is 16-bit, that too unsigned. If it is written with SH, then that is referring to half word 16-bit but signed value. This is normal word 32-bit data. Now if suffix is capital D, it is corresponding to double word, that is 64-bit, which is not supported by ARM Cortex M3. Next, push and pop operations are also considered as load and store instructions respectively, and these two are 32-bit stack operations, remember. And you know that for every push operation, this stack pointer register get decremented by value 4, and for every pop instruction that get incremented by value 4, remember. So you are loading the content into stack, that is push, from the stack memory, that is pop. So you are loading and you are storing. So this is how push and pop operations also belong to load and store instructions of memory addressing mode. Now we'll see the execution using KEIL software of the same instructions which I have taken. Already those instructions I have typed here. So let's compile them. I'll show you how the contents are moved to the registers and how load and store instructions works. So this is that register bank, and this is referring to memory address. Okay. So let's start the execution line by line. So you can see now it is already pointed to line number 9. First instruction got executed, that is move R0 comma this immediate value. So R0 is already loaded with this value in 32-bit format like this. Okay, now we'll execute this line of the code, that is move R1 comma this hash inside the single quote capital A. So here ASCII value of capital A, that is 41, is moved into register. Let's see. This is how this value get updated into register R1. Next we'll see the next instruction, the movement of this immediate value into R3. See this. Now we have a decibel number. It will be saved in hexadecimal by converting decibel into hexadecimal. So hexadecimal value of 100 is 64. So let's see the execution of this. R4 is loaded with this value, that is hexadecimal of 100. Next we'll see the register to register addressing mode. The content of R3, that is this value, is moved where? R5. R5 is already having this value, so R3 content is moved to R5. So let's see how this movement will take place. So you can see this R3 value is loaded into R5. Okay, next we'll see move W and move T instructions. So here move W does what? This value will be loaded from LSB to MSB into R0. So already R0 is having this value, so this value is overwritten. Let's see how it get executed. So you can see from LSB side this immediate value is loaded into R0. Next we'll see thumb. So here it is moved from MSB to LSB. So here you can see the movement. So previously 0041 was already present. There is no change with respect to this part. Only it is loaded from MSB, and the remaining all were 0 plus previous value. Okay. Now we'll see one more thumb with the register content R0 itself. So already here we have 0000. Upon the execution of line number 18, this value will be loaded in place of zeros. So let's see now. See, after the subsequent execution of move W and move T, this is the content of register R0. That is what we have discussed. Next, same move instructions. Now we'll see load instruction. So the same example I have taken. So referring to the content of R1, that is this itself is what? Memory address. So I'll copy this address. I'll go to memory and there I'll paste it and say enter. Now you can see the starting address of the memory is pointing to that address of R1. Now what you are doing? What content is present here? The content is 00000000. So this is 32-bit data. This 32-bit data is 0, and this 0 is moved where? R5. R5 is already having this value 0x401234. So this is written as 0 now. Let's see. See, you can see here. So at this address of R1, this 32-bit data is moved to R5. So how it is moved? 000000 and 00. Like this it will be moved to this address or register R5. Okay, now we'll see with offset. So now the memory address is what? Register content R1, that is this, plus 4. If I add 4 to this, it will be A04. Go to memory, write 4 there. Now it is pointing to which address? R1 plus offset value. So that is the address now. Say enter. Again that value is 0. 32-bit value is 0. And this 0 is loaded where? R3. Check whether R3 is having any value. This need to be made 0. So let's see. See, this R3 content is made 0. Now we'll see this is pre-indexing. Now we'll see post-indexing. Okay, as I told you, first it will perform normal load execution, and that that R0 is updated with R0 plus offset value. Okay, now we'll see the register R0 value, that is this. Okay, so at this location I'll copy this. Now this is referring to memory address, paste, say enter. Now it has some value, so this is 32-bit value. So 32-bit value will be read like this: 10000268 from MSB to LSB. I repeat, from MSB to LSB this value will be read like this: 10000268, and this value will be loaded where? In R1. So let's execute the code. So you can see here, this value, 32-bit value, is loaded where? R1. This value is loaded into R1, that is done. How this value is read? 100002 and 68 from MSB to LSB. After the normal execution of load, I told you R0 value, that R0 content before it was 0 is updated with R0 plus offset value. R0 is 0, offset value is 4, 0 plus 4 is 4, so that is what is updated. So same operations will be with respect to store, but in the exact opposite way. Okay, so this completes the basic class on instruction set of ARM Cortex M3.